Right now we're going to focus on how to identify acids and bases. There are three primary definitions for what constitutes an acid or a base. The first one is what's called the Arrhenius definition. So you can see Arrhenius definition right here. The second one is Bronsted-Lowry, and we're going to talk about that next. And the third one is what's called the Lewis definition. We're going to save the Lewis definition for another video. The Arrhenius and Bronsted-Lowry definitions tend to be most convenient for aqueous solution, whereas the Lewis definition is often used in organic solutions or things where you do not have water as a solvent. So all three are useful, and none of them contradict each other, but Bronsted-Lowry is a little bit broader than Arrhenius, and Lewis is a little bit broader than Bronsted-Lowry. So let's start with Arrhenius, which is this very simple definitions of acids and bases that we learned back in 1211. An acid is a substance that produces H plus ions in aqueous solution. So we have our example here with HCl breaking apart to produce H plus and Cl minus. Now, we I very rarely write the equations like this, because in aqueous solution, this H plus really never hangs out by himself. What happens is an H plus ion sees a water molecule, and this H plus, he has no electrons whatsoever, whereas water has these two lone pairs, and they happen to get together and form what's called hydronium. And so you'll have the water, but now it's got three hydrogens, just that one lone pair, and a positive charge. So in aqueous solution, you're not really going to find any H+, you're really going to all find it in the form of H3O+, and so you'll often see the equation written like this instead. HCl reacts with water, and it gives it a hydrogen to make this H3O+, and leave behind that chloride ion. Base, on the other hand, substance that produces hydroxide ions in aqueous solution. So for instance, sodium hydroxide will break apart to form sodium and hydroxide. And hydroxide will hang out by himself. He has no problem with that. So we can see that for acids, the main thing is that you produce this hydronium ion, whereas for bases, the main thing is that you produce this hydroxide. So acidic solutions are characterized by how much hydronium ion they produce. Base solutions are characterized by how much hydroxide they produce. Now that's the Arrhenius definition, and the Arrhenius definition is pretty strict. There's a limited number of compounds that can count as acids and particularly as bases in the Arrhenius definition. In the Arrhenius definition, you really have to have that hydroxide group directly tied in to your chemical formula. The Bronsted-Lowry definition kind of relaxes that restriction a little bit. In the Bronsted-Lowry definition, we instead just think about that transfer of an H+. So an acid is an H+ or proton donor, whereas a base is a proton or H+ acceptor. And the reason these two terms, proton or H+ is interchangeable, is because hydrogen only has one proton and one electron normally. He does not have any neutrons. So when you form H+, you literally just have a proton left. So we just refer to him as a proton. This definition really broadens things. Again, not so much for acids, right? This equation looks pretty much just like we had before. And again, we can think about that HCl donating his hydrogen to the water to produce this H3O+, and that's what makes him an acid. Not so much that I produced this, but the fact that he donated that hydrogen. However, if we look at this second one, we can see NH3 does not look like one of the base, or does not look like the base we just looked at, but he can accept a proton from water, so water can give him a proton to make NH4+, leaving behind this OH-. So once again, acids produce hydronium and bases produce OH-, but we're looking at it in a slightly different way. So this really widens the definition of acids and bases, and is a very, very handy definition. This is the one we're going to use 98% of the time. Notice, interestingly, that in this equation, water accepts the hydrogen, and that makes him a base. Whereas in this equation, water donates the hydrogen, and that makes him an acid. So water is pretty unique in that he is amphoteric, meaning he can act as an acid or a base. And several different molecules can do this, and we'll learn to write equations for amphoteric molecules. But it's important to note that water is going to be very, very useful to us because of this amphoteric property. So let's use these definitions to try and, I'm skipping ahead of myself. Let's think about conjugates for a second. So keep in mind that most of these reactions are going to be reversible reactions. So they could either go in the forward direction or they could go in the reverse direction. So if we think about this equation here and we try and identify who my acids and bases are, we can say, okay, if I look here from HF and H2O goes to F minus and H3O plus, HF must have donated a hydrogen to H2O. So that would make HF my acid and that would make H2O my base. Now, on the other hand, let's think about the reaction going in reverse. In this case, it must have been the hydronium, the H3O plus, that donated a hydrogen to fluorine to produce the F minus. So in that case, H3O plus is my acid, whereas F minus is my base. So we can see in the Bronsted-Lowry definition, we always have what are called conjugate acid-base pairs. So here, HF and F minus are a conjugate pair. My acid donates a proton to become my base, and then that base accepts a proton to become my acid on the other side. And same thing with water and H3O plus. That's another conjugate acid-base pair. So in a Bronsted-Lowry definition, you'll always have an acid and base on the reactant side, but you'll also have an acid and base on the product side, and we can break them apart into these two conjugate acid-base pairs. All right, now let's try and apply this definition. So for each of these reactions, let's identify the acid and the base. And I usually find the Bronsted-Lowry the easiest one to consider. So if we look at this first equation, pretty straightforward. We say, okay, I have HNO3, and I have NO3 minus here, so this must have donated its hydrogen. So that's going to make HNO3 my acid. It's going to make H2O my base. I'm going to try and look for my conjugate pairs as well. In order for NO3 to turn into HNO3, the hydronium must have donated that hydrogen. So over here, this makes H3O plus my acid, and NO3 minus my base. So I have my two conjugate pairs here. Alright, now let's try the second one, same idea. So if I look at this and compare it to that guy, I can see, well, he must have gained a hydrogen, so H2O must have donated a hydrogen to CH3 and H2, so that in this case is going to make H2O my acid, and it's going to make this guy my base. Looking at it the other way, in order for my CH3NH3 plus to turn back into CH3NH2, he would have to get rid of a hydrogen. He'll give it to hydroxide to form water. So in that case, this guy is going to be my acid, and hydroxide is going to be my base. So once again, I can identify my pairs. In addition to being given an equation and identifying acids and bases, we should also be able to write our own equations. So, for instance, HCO3 minus is amphoteric. Again, can act as an acid or a base. Write equations that demonstrate both its acidic nature and its basic nature in aqueous solution, so with water. Identify the Bronsted-Lowry acid and base in each equation, as well as their conjugate pairs. So we say, okay, we obviously have to write two equations, one where this molecule acts as an acid, and one where this molecule acts as a base. So each time, I'm going to set these up the same way. I'm going to take HCO3 minus, and I'm going to react him with water. Do my double arrow. And I'll just go ahead and set up this guy at the same time. And water, double arrow. So when HCO3 is an acid, he must donate his hydrogen. So that's going to leave behind just this CO3 minus piece. The other thing to keep in mind is that when H travels, it always travels as an H plus. So he always takes a positive charge with him. So instead of just being CO3 minus, I have to take away another positive charge. So it's going to be CO3 2 minus. Yeah, that's an AQ there. Meanwhile, that H plus travels over here and joins up with the H2O. So that's going to form my hydronium ion, H3O plus. So here, HCO3 minus was acting as my acid, water is my base, we can see that he donated a hydrogen and became the conjugate base, and this guy over here is going to be my conjugate acid. If we think about it in reverse, he'd have to donate a hydrogen to regenerate that HC3O plus. HCO plus. Nope, H said it right the first time. HCO3 minus. There we go. Alright, sorry, couldn't talk for a minute there, but we're back on track now. Okay, so that was the acid. So H2O3 acts as an acid, donated a hydrogen, and we have my acid and base pairs there. On the other hand, HCO3 minus could act as a base. He could take a hydrogen from H2O. And remember, it always travels as H+. And if we do that, he'd have not just one hydrogen, he'd have two hydrogens, so he'd be H2 and then CO3. And again, he travels as a plus, and I have a minus here, so right now those are just going to cancel out. And then he would leave behind from the H2O, OH minus, right? Take away an H plus, and that's what we have left. Throw my AQ on there. So in this case, water donated, so he was my acid. HCO3 minus accepted, he's my base. Over here, it must have gone the other way. H2CO3 would have to donate, so he's my acid, and over here, OH minus is going to be my base. So once again, I have my conjugate pairs. So anytime you're asked to write an equation showing something's acidic or basic nature, you just react it with water, and then think about either donating or accepting that hydrogen ion.